For our project, which includes Anthony, myself, Chris, and Tylee Nee, we have decided to demonstrate Newton's three laws. The first being that an object at rest will stay at rest unless acted upon by an outside force. The second part of this first law is an object is in motion will stay at motion unless acted upon an outside force. To demonstrate this, we have our experiment. Very similar to that of pulling the tablecloth under, let's say, just in general, whatever you want to put on there, let's say cups. It's very much the same concept. We have a nickel on the top of this barrier, which is Mr. On's pass. At the bottom, we have a cup. If Newton's law is true, if we remove this without accelerating this nickel, it'll drop straight into the cup, just as a cup or a plate under the tablecloth experiment will stay at rest, thus demonstrating his first law.
Right now I'm going to attempt to remove this barrier without giving any acceleration to the nickel, and if I do it correctly, the nickel will drop directly into the water. And here we go, we'll try one. And see, it didn't work. I applied some force to the nickel, so the nickel moved with the pass, and we're going to go for trial 2 here. And there you go. The nickel went into the cup because this barrier, my force from my hand to the pass did not affect the nickel at all because it was at rest. So now that we have successfully hit or successfully demonstrated Newton's first law, we have to explain why the nickel had dropped into the cup and why it didn't float in midair. So after we have knocked off the pass and the nickel is dropped into it, the only force, there was no second barrier to act upon the nickel, or to hold the nickel up, and thus the only force acting on the nickel was gravity, which forced it down into the cup. And now that the cup is resting, or now that the nickel is resting in the cup, the nickel is resting in the cup, the nickel is now at rest.
Because while it was on the pass, there was being two forces applied to the nickel. The first was normal force, which was pushing up, and the gravitational force pushing down. And when we remove that, it went in the cup. So now the only forces acting upon the nickel in the cup are the normal force from the table and gravity. Alright. Newton's second law states that the summation of forces, or total forces, equals mass times acceleration. Now, we're going to assume that this ball is 1 kilogram. Probably isn't, but it really doesn't matter. We're going to assume 1 kilogram. Now, we know that if the formula is true, it's force equals mass times acceleration, and we know the mass of the ball, 1 kilogram. We know that we're on Earth, so there's a constant acceleration going down. We are going to know that the force, or in this case, we're going to say the weight of this ball, would be 9.8 newtons. 9.8 meters squared times 1 kilogram equals the weight in this case, which is 9.8 newtons. Let's say we're on the moon, and gravity was entirely different. There was a different constant, 1.6 meters per second squared. Now in this case, we have 1.6 meters per second squared times 1 kilogram, which equals 1.6 newtons. Newton's third law states that for every force there is an equal and opposite force. Now, for our example of this, we're going to use two standard tennis balls. I'm going to use my hand to apply force to the first tennis ball. Now, it hit the second tennis ball with an equal and opposite force. Now, this may seem a little strange because the force that hit this tennis ball seems less than its original force as I was pushing it. Now this can be due largely to friction, the friction of the table as the tennis ball moves along. If we were in a frictionless environment, then the force of these two balls hitting each other would have been equal, thus demonstrating Newton's third law.